In the next example, we're going to construct an antiderivative graphically. But before we do that, let's step back and think about what a function tells us about its antiderivative, right? So if we have a function capital F, and we know that it's the antiderivative of lowercase f, that means that if I take the derivative of the antiderivative, right, I should get the function back, right? So that means capital F prime is equal to lowercase f, right? So that means that essentially if this lowercase f gives the slope, slope of capital F at any point. Okay, so all right, so if lowercase f is greater than 0 on an interval, right? Lowercase f is f prime, right? So that means that then the the uppercase f is increasing on that interval, right? Because lowercase f is f prime, right? So then the derivative is positive, and that means that capital F is increasing. Now, if lowercase f is negative, right? If it's negative, remember, okay, again, that this is f prime, and if that's negative on any interval, then capital F is decreasing. Okay, so capital F is the antiderivative. And if lowercase f is 0, again, that's f prime, so on an interval, then capital F is constant. Or, you know, it's a point where it's changing from increasing to decreasing on that interval. Okay, so let's go ahead and take a look at the next example. Here, we're given, we're shown a derivative, capital F prime. Remember, in that last thing, I was referring to this as lowercase f, but I'm just going to call it f prime because I think, or capital F prime, because I think that'll be more clear, right? If I think of it that as that function as the derivative, and I want to construct the antiderivative. Okay, I've given f prime, and I want to construct the antiderivative, and I'm told that capital F of 0 is 10, and we want to sketch a graph of capital F of x, right? So we're taking the derivative and we're going to construct the antiderivative. So the first thing I want to do is I want to construct a table of values. All right, so I'm going to just make a little table here with f and f, capital F of x, and I'm told that when x is 0, f of x is 10. Okay, so this one is given. All right, now I can find more points. If I look at the graph, I'm given the areas. Okay, now I don't necessarily want to have to estimate what f at 1 would be. So I'm going to, the next value of x where it's easy to find the value of capital F of x is at 2, right? Because I know that the area from 0 to 2 is, I'm given that it's 14, right? So what I can do is I can just take f at 0 and add the integral from 0 to 2 of f prime of x dx, and I'll get 24. All right, so there's another point on my antiderivative. Okay, and I can just keep doing that. So the next point where it's easy to find the value is at 5, right? Because I know the integral, right? I know that the integral is 20, or sorry, the area is 20, but it's below the x-axis, so it's negative. So I'm going to take f at 2 and add the integral from 2 to 5 of this f prime of x dx. All right, now I've got to remember that it's negative, so I'm going to subtract 20 from 24. I get 4. All right, and then I notice this should be a capital F right here. All right, and then I'll find the value of the antiderivative at 6, and I can do that essentially by taking f at 5 and then adding the integral from 5 to 6 of this f prime of x. And I'm given that area is 12, so if I add that on, I end up at 16. Okay, so now I've constructed a table of values. These are values for that are on the graph of the antiderivative. All right, so I'm just going to plot those points down here on the graph. And so let's see here. I'll scroll up a little bit. So I have at 0, I'm at 10, right? And then at 2, I was at 24, so maybe that's about here. And then at the next one is at 5, I'm at 4, so about here. And then at 6, I'm at 16, so about here. Okay, so now I have some points on that I know are on my graph of the antiderivative. Now, before I just connect those up with some curvy lines, I'm going to get some more information from the graph of the antiderivative. All right, so I'm going to scroll back up here a little bit. And because I can tell from this graph, I can also tell the concavity. I can tell the concavity. Now, how do I know about the concavity? Well, I know that f double prime is the slope of f prime, right? And I have f prime here, so if I look at the slope of the derivative, I get the second derivative. Okay? So so I can see where the slope is positive and where it's negative by looking at where f prime is decreasing and where it's increasing. So let me get a highlighter here. I'm going to use pink for negative. All right, and I can see that the slope is negative for this portion of the curve, right? So what is that telling me? That's telling me that f double prime is negative. So so f is concave down, right? So f is concave down over that interval until about, I don't know what that is, about a little over 3.5, right? So it's got to be concave down. And let me change colors here. And so then I can tell also where the graph is increasing, right? It's increasing for this section of the curve. And so that tells me f double prime is greater than 0, which means that the antiderivative has to be is concave up on that section. Okay. All right, now, so if you think of this as the derivative, I know this is also the critical point. This is a critical point. This is a critical point, right? Because the derivative is 0. And then I have this point down here where it's changing concavity, right? So this is my inflection point. So I'm going to label that IP, right? And because f double prime is equal to 0 at that point, it's switching from negative to positive, right? So the concavity is changing. So I also know an inflection point. All right, let's try to incorporate all of that in the graph down here. All right, so I have an inflection point that's somewhere, about a little more than 3.5, and I don't really know the y value, but I'm just going to mark a point here that's kind of in between my, the points that I know. I think this one's wrong, isn't it? I've meant to mark it at 2 and not at 3. So let me see here. Yeah, this should have been 2, 24. So that should have been here. So there's a point. Okay. So I'm actually gonna change this a little bit because I don't know where it is, but it's because if this is my critical point, right? This is the critical point. That's the local, and you can see it's a local maximum because my this derivative is changing from positive to negative, right? Increase, so f is going from increasing to decreasing at the point. This is also a critical point, right? Because if I look at the graph at 5, that's where the function is going from the derivative is going from negative to positive, right? So f has to be going from decreasing to increasing. So this is a local, write it down here, local minimum. And this has to be a local maximum, right? And then I have to have my inflection point has to be somewhere in between. So there at about a little over 3.5. So this is my inflection point, okay? All right, now I said that the graph of the antiderivative has to be concave down, right? It's concave down, and so it's going to look something like that. Okay, there's concave down, and then it continues to be concave down until that inflection point. Okay, so there's what my graph should look like. And then it switches to concave up. So beyond that inflection point is going to be concave up. So here it's concave up and decreasing. And here it's concave up and increasing. Okay, so that's a sketch of what my graph looks like. And it incorporates the proper concavity. All right, so like I said before, we have a local maximum at the point 2, 24, right? And we also have a local minimum at 5, 4. All right, because I think that's what they asked up here. Give the coordinates of the local minima and maxima. Now, I could ask you about the absolute minima and the absolute maxima. And in this case, given the interval that we have, these are also absolute minimum and maximum. All right. Now, remember, with absolute minima and maxima, we have to include the endpoints, right? We have to look at the endpoints, and in this case, the endpoints are low. Well, they're not. They're the lowest endpoint is not as low as the local minimum, and the highest endpoint is not as high as the local maximum. So we would choose the local minimum and that maximum as the absolute minima and maxima. So, but it could be, you could have a case where the endpoints are higher or lower than the local minima or maxima. Okay. All right, so let's kind of summarize what we incorporated concavity in that last example. So let's kind of summarize what we did here. So, okay, again, capital F is the antiderivative of this lowercase f. Okay, so that tells us that f prime is equal to f. Okay, if f is the antiderivative, if we take the derivative of it, then we get the lowercase f function. And we also know that if we take the second derivative, that's got to be f prime, right? We're just taking the derivative of both sides. So when we look at the lowercase f prime, what we're really looking at is the second derivative of the antiderivative. Okay, if it's positive, right? If it's positive, then f, right? F, lowercase f, which is f prime, is increasing. And the graph of the antiderivative is concave up on that interval. Okay, so remember that we looked at the slope of the derivative to find the second derivative. I think I lost that. Okay. And then, on the other side, if lowercase f prime is negative, right? Then we're looking at the second derivative of the antiderivative then. And so if it's negative, then lowercase f is decreasing. Lowercase f is decreasing, and that means that the antiderivative is concave down on that interval. Okay, now I think it's probably easier to see with the example. I feel like this using the lowercase f and uppercase f is just confusing. But so that's meant to summarize what we just showed in the example. But I mean the key thing is that that we can look at the slope of the derivative to find the second derivative of the antiderivative. Okay, so all right. So I'll meet you in the next example.